Eurolabs project offers transnational access to more than 40 European research infrastructures and brings together the three scientific communities of nuclear physics, detectors and accelerators for particle physics. The transnational access activities support small teams to carry out experiments and tests at these facilities. One of them is AIC-144 facility at the IFJ PAN in Poland.
My name is Paweł Olko. I am the coordinator of the cyclotron facility, AIC-144, at the Institute of Nuclear Physics in Kraków, Poland. This cyclotron was developed by the physicists and engineers of this institute for the eye treatment. After the proton therapy was completed, now it's used for irradiation of electronics and scientific experiments.
The Institute has over 60 years of experience in the construction and operation of cyclotrons. In 1958, a U-120 cyclotron manufactured in Kiev was installed. After its liquidation in the early 1990s, an AIC-144 isochronous cyclotron was installed in the same vault. The new cyclotron was entirely designed and built at IFJ to accelerate light ions, primarily for research in nuclear physics and radiochemistry. This AIC-144 was used until 2010 primarily to produce rare radioisotopes for scientific purposes. Later, its design was modified and optimized to produce a proton beam with an energy of 60 MeV and a current of 80 nanoamperes, stable to within 5%, for the needs of proton radiotherapy. In the years 2011 to 2015, 128 patients with eye cancer were irradiated with a 60 MeV proton beam from the AIC-144 cyclotron. The AIC-144 cyclotron is currently operated as a user facility for research and development purposes in the fields of radiation physics, dosimetry, medical physics and radiobiology. The machine is fully serviced by our experienced technicians and engineers. The cyclotron team also provides assistance and advice in preparing scientific experiments. The accelerator operates almost all year round, with maintenance only lasting 2 weeks during the summer holidays. The in-house developed beam delivery system and treatment room facility were all designed and built by engineers, technicians and software developers at the IFJ PAN. There are currently 2 lines of beams that are offered for experiments to external users. High-intensity irradiations are performed in a well-shielded experimental room, mainly to test the radiation hardness of electronics, test new detectors for the innovative flash proton radiotherapy and perform intensive irradiations for materials science. A solid, stable irradiation stand with a 2D scanner allows for uniform exposure of large pieces of electronic equipment. The configuration can be easily customized and adapted to the user's needs. The irradiation can be performed with a dose rate of 40 grays per second. Precise small field exposures are performed at an irradiation line in a former eye treatment room. The advantage of this line is the ability to create a uniform depth dose distribution, so-called spread-out Bragg peak. A beam with a diameter of 40 mm, scattered at a distance of over 10 meters from the isocenter, is perfectly uniform. Thanks to a set of collimators, the beam size can be reduced up to 1 mm in diameter. Additionally, positioning using lasers and X-rays can be performed with an accuracy of a fraction of a millimeter. The line offers high-precision medical-grade dosimetry, with a link to the secondary standard dosimetry laboratory.